Hi there, I'm John Michael with GMAT Ninjas, and welcome to the Exponents video. First things first, is this video for you? If you are still learning exponents, if anything up here looks in any way unfamiliar, rules for manipulating exponents, some of these stranger exponents we can see, if any of that's unfamiliar, press pause, get up to speed on your exponents, come on back. I'll be talking through some of these things, but I will not be explaining them from the ground up. I'm expecting you to have the math so that we can do the quant. This video is for you if you've learned the math and are looking to bring that into GMAT quant type questions, and this video is probably also for you if you're doing pretty well but want to do better. We're going to start relatively straightforward, and difficulty is going to increase exponentially. By the time we're done, we will have met some difficult questions. There's no data sufficiency in this video. With data sufficiency now a part of data insights, we really aren't seeing exponents as a math topic that's covered there. So everything you're going to see in this video is a quant type question. And with that, let's see a quant type question. Here it comes. I'm going to put it on the screen for 2 minutes. 2 minutes is your target time for a question in the quant section. On the other side, I'll see you again. If you want more time, you can pause the video. Otherwise, we'll take it apart and see how it works. Here you go.
Hey everybody, Charles here. Sorry for the interruption. Before we get you back to that quant content, 3 quick things I'd love for you to be aware of. First of all, this video is part of our full, free, complete GMAT course that's available up on our YouTube channel. If this course is saving you money that you would otherwise spend on a course or a tutor, please consider donating some of that savings to charity, either a charity that you love. If you don't have a charity that you love, we've got a list of charities that we love to support on our website, gmatninja.com. Second thing, if you love that presenter that you're watching in this video, not me, the other one, they offer one-on-one tutoring. If you're interested in that, gmatninja.com and we can set you up. Third thing, finally, if you're doing great on the GMAT, doing great on the GRE, starting to look for admissions help with your applications for grad school, we would love to refer you to a bunch of our favorite companies. So just hit us up. There is a contact form on our website, gmatninja.com. Also, a link in the video description. Just fill that out. We'll send you a list of our favorite admissions consultants, not just at our company, no strings attached, not going to sell your email, not going to try to sell you anything. We just want to make sure if you've put in the hard work on the GMAT, that you end up in the best possible hands if you need help with your applications. All right, that's it. Enjoy the quant.
Okay, that is 2 minutes. If you are still working, pause the video. If you're ready to go, let's talk about this. First thing we do, we read the question. Second thing we do, we read the question again. If it's a short question, it costs us nothing to read it twice. If it's a long question, those are precisely the ones we're most likely to miss out a detail on. We read a question twice, every question. Save yourself having to think about whether it's a question worth reading twice. Read every question twice. In this instance, what have we got to work with? We have an equation. It's got a single variable in it. It's got a whole lot of exponents and a few other slightly weird things. What are we here for? Well, the question's asking for the value of x. I like to put to one corner what it is I'm looking for. X. No big surprise. First thing we're going to do is write this down on our yellow pad, our whiteboard, whatever you might be working on, and be certain that, especially with something with lots of bits and pieces like this, that you are copying it down correctly, accurately. If we make a mistake in our transcription, we don't stand much of a chance of getting the question right. What do we have here? Single variable equation, okay, fine, and lots of exponents. We have rules for dealing with exponents, hurrah. Those rules really only come into play when we have common bases. And at the moment, we have a mix of 9s and 3. So let's get them into a common base. We know very well that 9 is 3 squared. So wherever we see 9, we're going to pop in 3 squared. And then we're going to be in a common base situation. Let's have a look here. This is a little bit peculiar. We now have a squared term inside of a cube root being raised to a power. It doesn't really feel like we have the rules to deal with this. So let's take the given information and rewrite it in a format that's more useful to us. The roots are fractional exponents. If we are talking about the square root of y, we are talking about y to the 1/2 power. Similarly here, the cube root can be rewritten as the 1/3 power. And all of that is being raised to the 6th power. A bit unusual, but we are in a position where we can multiply up. A power raised to a power gives us a multiplication. If you want to see that in full, that's something like that. 1/3 and 6 cancel to make 2. We are talking about 3 to the 4th over here on the left-hand side. On the right, a power raised to a power gets multiplied. And we're going to leave this as it is for one more line. When we multiply the same base, we add the exponents. And just copying that once more. Think about what we've got here. How do we solve for a variable that is up in an exponent? Well, think about what this is telling us. 3 raised to this crazy power is 3 raised to the 4th power. They're the same thing. So we can really let go of the base entirely and say that this crazy power, whatever it is the same thing as 4. Single variable, single equation, absolutely no problem. Bring the 10 across, subtract 10 from both sides. We'll have -6 over here. -6 is -6x. Divide both sides by -6, and we can say that x is 1. And that is our answer choice C. Read the question one more time. Make sure we didn't leave anything out and found the thing we were sent in search of. We dealt with all of that. We dealt with all of these, and we have a value for x. We're happy people. All right. You're warm. Here comes question 2. Okay, that is 2 minutes. If you are still working, press pause. If you're ready to talk about this question, let's talk about this question. First thing we do, we read it twice. We've got something kind of peculiar. We've got fractions, we've got negative exponents, we've got negative signs running around. Okay, we've read it twice. We're clear on the situation. We don't really have an ask here. We're finding another way to say it. We are simplifying the expression, re-expressing the expression. First thing I want to do is copy it down onto my yellow pad, my whiteboard, my piece of paper, and I'm going to be very careful to copy it just as it appears, and in particular get all of these negative signs right where they belong and nowhere else. Okay, I've got exponents. I know that I have rules for exponents. Super. To use those rules, I want to have the same base. Okay? What are my options here? Well, there are a couple ways to proceed with this question. There are a couple ways to proceed with every question. In this instance, I might think, okay, well, let me get to 3. Clearly, everything here is related to the number 3. And I can come on through and say, well, 1/3 is 3 to the negative 1. Put that in where I see a third. Everything around it stays in place. 1/9. Again, okay, that's 3 to the negative 2. And I want to be sure that I get my negative sign in the right place. That's getting raised to the negative 3rd power. Notice the difference of the placement of the negative sign. And over here, a bit less trouble. 1/27 is 3 to the negative 3rd power, and that's getting raised to the negative 2. Okie doke, I'm ready to go. There are options, there are possibilities. You might look at this and think, maybe that's a step you don't care to take, because we can express these terms as they relate to 1/3. So we can leave that 1/3 term exactly as it appears. What is 1/9 but 1/3 squared? And 1/27 is 1/3 cubed, then getting raised to the negative 2nd power. You can proceed in either of these ways. They both work. They both get you to the correct answer. You might have a look at the answer choices and say, well, unless it's something really peculiar, it looks like we're dealing with fractions raised to negative exponents. You might want to proceed in this way over here in black. 2 paths. If you do them right, either one gets you to the correct answer. I'm going to proceed over here. I personally feel my feet a little more on the ground underneath me when I have that friendly integer. So let's talk about what I've done here in blue. I have a power raised to a power. I'm going to do a multiplication. Negative 1 multiplied by negative 6 gives me 3 to the 6th. And this negative sign tells me that that term is negative. That's completely different from the negatives on these exponents. I multiply them up, and a negative times a negative gives me a positive. But that negative sign out front tells me that this is a negative number. And I'm going to go ahead and put in little multiplication signs, because as these negative signs turn up, we're not doing subtraction, we're doing multiplication. In this instance, once again, I'm going to multiply up a power raised to a power, negative 2 times negative 3, positive again. And that is, again, negative. What we have here is a positive number. Anything raised to an even power is positive, and that applies even if it is a negative even number. And when we think of the even numbers, we think 2, 4, 6, 8, 10, 12. Negative 2, negative 4, negative 6, negative 8 are also even numbers, and so is 0. This is a 3 raised to an even power. It's positive, but the negative sign comes out here. It is negative. If we had raised it again to an even power, it would become positive. That's not what we're doing. We're raising it to an odd power. It stays negative. And our last term, multiply up. How about that? We've got 3 to the 6th once again. Now, we're in a pretty happy situation. Are we really multiplying a common base, though? I've got 2 negatives, 1 positive. Yes, when it comes to using these rules of exponents, on the one hand, I have my 3 to the 6th, which I'm doing 3 times. And on the other, I have a negative times a positive. That gives me a positive. I can even indicate so if I like. So what we have here is 3 to the 18th, which doesn't really look like any one of our answer choices. It looks a little bit like this one, but that's a huge difference in exponent. And if I stop and think about it, 216 is going to be 6 times 6 times 6, there to catch out anyone who misunderstands the rule. When we're multiplying terms, we add the exponents. So which of these beauties is this? Well, thinking about where we started with these fractions raised to exponents, we might want to get back to those terms. 1/3 to what power? Well, 1/3 is 3 to the negative 1. What would we raise that to in order to get this? The missing number here is negative 18. So we've got 1/3 raised to the negative 18th power. Okay, a bit closer to some of our answer choices. I'm going to go ahead and dispense with E. 1/3 to the 6th, 1/3 to the 12th, that is not the same thing. And we're left with 2 answer choices that don't really look like what we want. Hopefully, one of them is equivalent. 1/9 to the negative 9th power. Well, 1/9 is 1/3 squared, and you want to raise that to the negative 9th. There we go. Power raised to power. That's what we're looking for. Once again, you can proceed dealing in terms of 1/3. You'll notice that having sort of flipped them from fractions to integers, I now kind of have to flip them back to evaluate these fraction terms to find a match in the answer choices. If you proceed like so, you won't have to flip back because you never flipped in the first place. If you proceed with fractions, Lord love you, just know what you're about and make sure your workings are the right end up. This will work. It'll get us to the exact same place. C is our answer choice here. Now you're fully warm. See how you do with the next one. That's 2 minutes. Pause if you need to pause. Let's talk about the question if you are ready to talk about the question. I read it again. It feels a little bit peculiar. I have rules for exponents, but I don't have rules that apply when I'm adding things with exponents. I'm happy to see a multiplication with a common base, but this is addition and the rules don't apply. So I'm going to start by copying it down nice and carefully. 4 to the 5th plus 4 to the 5th plus 4 to the 5th plus 4 to the 5th equals 64 to some x power. And not a whole lot to say here, but what they want from me is the value of x. Okay. Now I've got to pick a path. I've got to figure out how I'm going to proceed from here. And this is where the GMAT gets good, because the previous questions, well, we've had rules. The second one, maybe it wasn't clear quite how to deploy them, but it's straight out of our toolkit of rules for manipulating exponents. And now I don't actually have a relevant rule. I mean, I can express my 64 in terms of 4. That's not a bad idea. Let's start there. And if I'm unclear, 4, 2 4s is 16, and another 4 is going to give me that 64. So this is 4 cubed raised to the x power. Great. I've done what was easy, and now I have all of this to deal with. Something the GMAT will reward us for is spotting opportunities to factor. And when we see an expression that involves distribution, it's almost instinctive to do the distribution. It's not quite as obvious when we have an opportunity to factor that we can do the same thing backwards and express it like so. Not always obvious or instinctual, but something worth doing. So I'm actually in a factoring kind of situation here. I have 4 terms joined by addition, and they all have something in common. Namely, they have 4 to the 5th in common. If I factor that out of each one of them, what's left behind is, well, 1 and 1 and 1 and 1. An odd sort of a maneuver, but add this up and we've got 4. I'm going to go ahead and power to a power is a multiplication. Just going to go ahead and write my right-hand side like so. And now I have my rules for exponents back, because now I am multiplying a common base. And there are all sorts of things that are invisible in math, and anytime we want to consider them, we can go ahead and write them in. 4 is 4 to the 1st power. If we ever want to write that 1 in, we certainly can. And now we're in a situation where multiplying the same base lets us add our exponents. And as with our very first question, we can kind of let the base go. Apparently, raising 4 to that power is the same thing as raising 4 to this power, so forget the 4s. 5 plus 1 is 3x. 6 equals 3x. X is 2. This move here is not necessarily obvious until you meet it. And now that you've seen it in action, it's a thing to remember. I'll also mention that I never get tired of thinking in terms of first grade and learning the very beginnings of math. If my first grade teacher told me, you have an apple, and we give you another apple, and we give you another apple, and we give you another apple, what do you have? Well, you have 4 apples. we can bring a first grader's understanding to this. If I give you 4 to the fifths, what do you have? Well, I have 4 to the fifths. That doesn't seem terribly mathematical, but it is perfectly true and exactly the same thing we find by being diligent and factoring things out. It can be really useful to take a step back, to express to yourself the very simplest things. I talk to myself all the time like I'm 5 years old, and I like to be absolutely clear on what's going on. Counting apples is as valid a way to get here as going through the mechanical mathematical steps there. Exercise 2. Happy day. Here comes another. That's 2 minutes. Pause if you need to pause. Otherwise, let's talk. I read my question twice. I've got a condition. The numbers are integers. Okay. I've got an equation. I've got a 2 variable equation. Ooh, 2 variables in 1 equation. Don't like that. And I'm being sent in search of A plus B. And in algebra, sometimes we can be sent in search of a combo, and we can find them together without finding them separately. In a case like this, we are probably going to find A, going to find B, and add them up. Let's see how we get on. We're here for the 2 of them together. Read it once again as I copy it down, being, as ever, super careful to copy the question that's written and not invent anything or leave anything out. Okay, and then I want to think about what I'm going to do to turn this into my values of A and B. And a couple things look strange. I have a subtraction on the one side. I've got a multiplication on the other. Okay, that's a little odd. And the numbers I'm looking for are the exponents. And when I see something like this, 2 to the B, this is representing some number. How many 2's are in that number? It's 75 times some number of 2's. It could be 150, in which case there's a single 2 and B is 1, or it could be 300, in which case there are 2 2's. 75 times 4, and B's are 2. So when I get this type of question, I start thinking about how many 2's, in this case, are there in the number in question. And I'm going to pull on that thread a little bit. How many 75s are there in this number, whatever it might be? Or since I've got a multiplication, I might break this apart, because 75 is 3 times 25 and some unknown number of 2's. And of course, 25 is 2 5's. So the mystery number on the left is made out of 1 3, 2 5's, and an unknown number of 2's. Okay, a bit strange. What can I do with this? Now that I've done the easy bit, I'm going to tackle the messy bit. I've got a common base. I'm not in a situation where I can add my exponents. I don't have multiplication, don't have a division. What am I to do? Well, the previous question, we saw factoring, pulling out common terms. And we can absolutely do that when it comes to exponents. If we've got 7 to the 4th plus 7 squared, we can think like so. We can pull out a 7 from each one of them, but, well, that still leaves common terms behind. We could take out 2 7's from each term, take 2 7's out of 2 to the 4th, and you've got 7 squared. Take 2 7's out of 7 squared, and you leave just a 1 behind. Okay, super, fine. Let's do something like that up here. Put some brackets around these terms, and what can we pull out of them? Well, as with the example, which I have ever so brilliantly erased, we can only take out as many 7's as are there in the lesser value. If I wanted to take out 4 7's, I would be smushing this into some kind of a fraction. Which of these is the lesser number? The subtracted one. So, although I don't know how many 5's that is, there's that many 5's in this second term, and there are more in this first term. When I pull 5 to the a minus 2 out of 5 to the a minus 2, 1 is left behind. When I pull 5 to the a minus 2 out of 5 to the a, how many 5's are left behind? 2. And suddenly I have fewer unknowns, I have a lot more knowns. Of course, here I have 25 minus 1, I have 24. And here I have 5 to the a minus 2. Think again about my right-hand side. I've already done something that looks a lot like prime factorization, that is prime factorization over here. So let me break this apart. 24 is 8 times 3. 8 is 2 cubed. 3 is 3. And we have a mystery number of 5's. And over here, we have that. So now I'm in a position to track down the value of my variables. Apparently, a minus 2 5's is 2 5's. I can say a minus 2 is 2, and apparently the number of 2's involved is 3. I can say 3 equals b. Add them up, and select my answer. The GMAT is going to reward you for identifying opportunities to factor. Some of them will look familiar, some of them will look a little strange, some of them might look very strange. When we take 2 fewer than a 5s out of this number, 2 5s remain. We've got some very exciting prime factoring going on here. I find this useful all the time to think about what a number is made out of, and to think about this kind of a question as how many? How many 2s are involved? How many 5s are involved? And we're going to find that out through prime factorization. All right, let's do another. That's 2 minutes. Pause if you need to pause. And if you're ready to talk about this, let's talk about it. I read it again. I think, oh my dear sweet Lord, what is happening here? Let me copy down my given information and let me identify what it is we're looking for, because we are not looking for X, and I almost kind of think I wish I were looking for X, because I'm in search of that, and I might not even know X by the time this is... Whew, oh boy. So we have a look here. We have a think. How to proceed with a question like this. I was just saying before, when I see these questions with exponents, I think they're asking me how many 5s are in this number here. Well, it's not going to be an integer of numbers of 5. We've seen that we can have fractional exponents, and we can have all kinds of fractional exponents. We can have, of course, 5 to the 1/2. That's root 5, a number just a little bit bigger than 2. We can have 5 to the 3rd, okay, no problem. But sure, we can also have 5 to the 3/2 power. We can have all sorts of things. We'd have 5 to the pi power. I don't know what that is or what that looks like. It's going to be a little bit bigger than this. But there are all sorts of numbers that could be there, and I don't think this is going to be an integer. This is not 5 to the 8th, and I don't know what 5 to the 8th is, but I can promise you it's not that, because this is an even number. It ends in 0. There's a 2 in it somewhere. It's not just made out of 5s. We get those little bits of information, like the previous question. They said A and B are integers. We have no such guarantee here. X is going to be something horrific. It's going to be some kind of irrational number, and if you're thinking about logarithms, let that go, you smarty pants. We don't need logarithms. We won't use them. We haven't got a calculator. We're going to think about this other ways. How many 5s are there in this number? Well, we can recognize something pretty familiar when it comes to 5s. I mean, I can tell you how many 5s are in 625, but it's not just 625, it's 625 multiplied by 100. That's another way of saying that number, and it becomes a little bit more graspable. And let's just check in. How many 5s is that? We start with 5, 25, 125. Okay, there we are. That's 5 to the 4th. Is that useful? Is that similar? Is that close? Maybe. And then we've got 100, which is one of our favorite square numbers. Nice and round, readily recognizable as 10 squared. But we've still got this very weird exponent over here. I want to get closer from where I am to where I want to go. And I've got some nice square numbers over here. I'd like to break this 8x down. And what I'm going to do, you can think about this in a few different ways. I'm going to take the square root of both sides. And although I don't know the value of x, I do know that the square root of a number raised to the 5x power is that number raised to the 4x power. I mentioned that I never get tired of talking to myself like I'm a first grader. We didn't do exponents in first grade, but remember that the square root is the thing that you multiply by itself in order to get the number in question. That's the square root of this one. And so then I can take square roots on the other side. Oh, it's a little bit more manageable, still a bit peculiar. And what is it that I'm looking for? Minus 2. So again, I don't want this many 2's. I want to take away 2 5's. And if I'm going to take away 2 5's, well then I'm going to divide them out, and all that remains is 10. Odd looking question. Not too bad once we get to the heart of it. Recognizing that division of an exponent by 2 is taking its root, and this notion of doing a subtraction within an exponent means having fewer of the number in question. What a treat. Here's another.
All right, two last things. Thank you so much for making it to the end of the video. If you've made it this far, you're one of those awesome people that's obviously really engaged in this GMAT thing. We would love your comments and your feedback. If there's anything else you'd love to see in our videos, hit us up in the comments. We'll do our best to oblige. Second thing, if you're enjoying it, hit that like button, hit the subscribe button. Helps other test takers like you find our full free video course. You need anything else? You know where to find us, gmatninja.com. Thanks so much. Enjoy this last question.
Okay, that is 2 minutes. If you want to pause, pause. And if you want to talk about it, whether that's because you've gotten to an answer or you're just tired of pushing it around the page, let's talk. I read the question. I rub my eyes in disbelief. I read the question again. I begin to weep, but then I find the steel in my soul and I confront this brute. There it is. Okay. What am I going to do? I'm going to copy it down. I'm going to make sure I have it right. I want to make sure I count these correctly. How many nines? I've got 6 nines. I've got 2 zeros here. This is a subtraction. And okay, now I've got 4 nines. And down here I've got 2 nines. Let's just estimate, right? Let's just do a little estimation. Call that 9 over 3. And call that 4 over 2. So that's 3 minus 2 equals approximately 1. Well, they're all really, really close to 1. Probably not exactly 1. Ooh, we're going to have to deal with this. Okay? Let's deal with this. I think about what in the world is going on here. And I might think a bit about the fact that it is pretty close to 9 over 3 and pretty close to 4 over 2, and consider that, well, those are square relationships. Okay. I might let my brain start drifting in some other directions. How can I express this? How not 9 is that? I mean, it's real close to 9, but it isn't 9. It's 9 minus 1, 2, 3, 4, 5, 1. Bit like so. And there are lots of ways to express this sort of thing. Those are my 6 places. So I could also call that 1 over. And thinking a bit about exponents, one more way to say that is 10 to the negative 6. And if I've got that, I'm saying the GMAT will reward us for spotting opportunities to factor. Another thing that we want to keep an eye out for, classic quadratics in unexpected circumstances. In particular, the difference of squares. And of course, 9 is a square number. So I have a square from which a square is being subtracted. Add it once, subtract it the other time. What's the square root of 10 to the negative 6? Well, we saw this on the previous question, where the root was half the exponent. And the same is going to be true here. The root is half the exponent. So that's another way to express the numerator on the left. And if I look at that, what is that but 3 plus a 10th 3 places over? Interesting. So that denominator's actually going to cancel out half of my numerator, and what I've got here is 3 minus 10 to the negative third. That begins to give me some ideas about how I might work with the right-hand term as well. How far off is this from 4? Well, it's 4 minus 1, 2, 3, 4 to 5. And I could potentially get myself into some trouble here, because I could certainly express that as, and then I could simplify that. 25 goes into 104 times. I'm not sure that's where I want to go. Instead, I want to think in terms of scientific notation here. This comes up sometimes on the exam, not a whole lot, but sometimes. This is 25 times 10 to the negative sixth. Because when we write a fraction this way, we can always write it as 2 pieces. Why not? So that's another way to express my numerator. Just like this one, where I have a 1 times, but we don't bother to write something like 1 times. So once again, I have a square from which a square is being subtracted. Square root of 25 is 5. Square root of 10 to the negative sixth is 10 to the negative third. And what's that all over? That's all over, well, look at that. We can see that that is also 2, from which 5 thousandths have been taken away. Once again, these two cancel, and what we have here is 2 plus, and what we're doing with them is subtracting them. I think I might turn these back into a more familiar form. Beg your pardon, that's 3 minus something, so it's not going to be greater than 3. That's my just barely less than 3. And this over here is my just barely more than 2. Do that subtraction, and all that is left is 0.994. That's my answer, choice A. It doesn't look very friendly, but there are some funny little details in these numbers which are going to hopefully give us the beginnings of an insight about where we can go with this. We spot the relationship between pretty much 9 and pretty much 3 corresponds to the relationship between pretty much 4 and pretty much 2. We might also notice that we have 6 spaces here and 3 spaces there. That also connects to the idea of squaring. And we might notice that this is off by 1, off by 1. This is off by 25, and this is off by 5. All 3 of those are clues to go in search of, to think in terms of squares, and then to go in search of ways to break squares apart. And a difference of squares is one. If the GMAT's going to reward you for spotting opportunities to factor, boy howdy, if you are so fortunate as to see a question of this difficulty, you're doing very well. And if in questions like this you're able to spot opportunities to break apart a difference of squares, the GMAT will reward you for that as well. Thank you so much. I hope you've found this video of use. Happy studying. If you have questions, alternative approaches, anything you want to add, there's your comments below. We do love to hear from you. Thank you so much. Happy studying.